once we have introduced this parameterization, let's look at these two covariant scalars. We can express these covariant scalars in this form. We simply have to substitute. We simply have to substitute in the forms that we already had, and we transform the density. You remember the density the way it was, just to understand. So this is clear. We had something like this: 4 pi rho equals m prime over r squared r prime. But now r is a times small r, right? And we have defined, we have also defined m is 4 pi by 3 mu r squared, right? So r prime is going to be a prime times r and times a, right? We just substitute everything. We have this is going to be the prime of this, which is first 4 pi third, then mu prime r squared plus 2 mu r. Okay?
Q.
No, sorry, here is q. So this is 3. Okay? This is going to be a squared times r squared, right? Just substitution. Now r prime is going to be a plus r a prime, okay? Right? Just substituting. Then this we can take 1a outside, and then the 4 pi's, what we have is now the 4 pi goes, right? So it is 1/3. Then notice that r squared will eliminate this one and this one, right? So we have 1/3, and then we can write this thing as mu. So mu. And then 1 plus. Well, you can see that we obtained that formula, brother, right? See, just 1/3 goes out, and then we have mu prime r plus 3 mu, and then here we have a cubed 1 plus r a prime over a. This one, sorry? Yeah, we take the 1/3 goes here and eliminates this one. We take this one here, we put it here. Right? And it's exactly the same. We write this as the product of mu divided by a cubed multiplying 1 plus r by 3 mu prime by mu over 1 plus r. And this fellow here we identify with gamma. Right? So this is what we obtain. So this is very nice because it looks like, let's compare this with the FLRW density. The FLRW density, which I write with a bar, it's a Friedman-Robertson-Walker object, right? It was something like right? So here, this one looks like that one, the first factor, right? Notice that if mu becomes a constant, this is 0. And if A becomes time dependent, this is 0. Right? So this looks like a Friedman-Robertson-Walker type of density that is multiplied times some factor. Okay? Now just for the sake of exercise, imagine that I tell you that mu prime over mu, which is dimensionless quantity, and is positive, while it can be negative, let's say something like this, is much smaller than, it can be negative because the gradient can be positive or negative, right? Let's say smaller than 1. Let's say that much smaller than 1. There is radial variation, but it's very, very tiny, very slow variation, right? So in this case, sorry? Yes, that's true, but it's multiplied times r to make it dimensional. Yes, now it's dimensional, right? Okay. So suppose we have this, then you can show that rho is approximately mu times AQ times something that like this. Right? Just do a Taylor expansion. So this resembles already like a perturbation, right? And it is, but however, if we write it like this, it's exact. It's not perturbation. If we make these assumptions, then it starts looking like a perturbation. And we connect to perturbation theory. But we're still not ready to do that because we don't know what's the covariant interpretation of mu. We don't know what's the covariant interpretation of this. So far, it's simply a coordinate expression. It's an expression that happens in this parametrization of the models. It happens like this. But it's already nice because this somehow has a nicer meaning than the previous variables did not allow this. They hide this. But if we change the metric variables, the metric functions, the way we have done, it looks like a Friedman-Robertson-Walker model with extra terms. These extra terms, they convey the inhomogeneity of the models. Okay? So this is already a nice thing. What about the psi2? The psi2 also looks like, the psi2 also looks like it's something, the difference between, see, notice, the psi2 is making a comparison between the factor that looks FLRW and the real density. See? Mu divided, this thing, 4 pi, this mu must have units of energy density. it's an energy density, right? It has units of energy density. And its rho, it also has units of energy density, right? This mu divided by a cube is, we know a cube is dimensionless, but mu has units of energy density. So we are comparing the psi 2 is giving us a comparison between a density that looks strikingly similar to the FLRW density, right? And the real density of the models. So psi 2 is already a sort of perturbation term, right? In fact, the expression there is given there. And if we make a series expansion, you can see that psi 2, say, it's already a perturbation term. This is important because what is psi 2 for FLRW models? Psi 2 is the eigenvalue of the electric Weyl tensor, right? For Friedman-Robertson and Walker models, the Weyl tensor is 0, right? So the non-zero, the fact that psi 2 is non-zero is one of the things that makes FLRW models distinct from FLRW, right? And we can do an expansion, like we have psi 2 equals 4 pi mu, let me copy that, it's by 3. By 3 a cube minus
1 plus r by 3.
Sorry, what? Minus the same thing. Because this thing. So I don't know if I wrote it. Maybe I made an error here. Because it's psi 2 by this thing minus. Let's do it carefully. Minus 4 pi by 3 rho. Okay. But we already know that rho is mu divided by a cube 1 plus. We already did this. Right? So we substitute this, and then we get psi 2 equals, well, the 4 pi over 3 is a common factor. So it's mu by a cube, and then we have to subtract. It's also common, so we can. It's also common factor mu by a cube, and then this will be 1 minus 1 plus r cube mu prime over mu. Perhaps I didn't write it correctly there. Okay. Okay. So we do the fraction itself. The ones go away, and this is going to be equal to minus 4 pi by 3 mu a cube, and then the r is a common factor here.
plus 4 pi by 3.
Sorry?
Plus 4 pi by 3.
Where?
In front.
In the last expression?
This one?
No.
Just negative.
Plus 4 pi by 3.
In front,
No
minus.
negative sign.
Ah, yes, there is a 3 here. There is a 3 here. Right?
So this is plus 4 pi by 3 mu by a cube r a prime by a
Yeah.
minus of mu prime by a.
Is it minus?
This is plus.
This is okay.
This is plus.
Because it's minus minus.
No, she is telling the
Minus.
initially you written minus, no? Yeah,
Here?
yeah.
Yes, it's here.
No, but minus is needed
So,
here.
but this should be plus 4 pi by 3. And
Somewhere.
then we have
Ah, yes, that's true. Okay. So, okay. So, we have something that. Right. So, if we make this assumption, then this is a very small quantity. Right? If we make this assumption here, this would be equal to 4 pi by 3 mu over a cubed times something that is small divided by something that is 1 plus small. So this is really a small quantity multiplying this, right? Notice that with the density that didn't happen. With the density we get something that is the FLRW form times, see this is mu over a cube times 1 plus small. And here we get something that is really like this. Okay? So psi 2 is the density has two parts. One part that looks like FLRW multiplied times some correction. But psi 2 is a correction itself, right? Which is expected because psi 2 is 0 in FLRW models, but the density is not 0. In FLRW models, the density is not 0. But the psi 2 thing is 0, right? So here we can identify, there are four covariant quantities that characterize the models.
Here, how can you say that this next term is very small with regards how?
Yes, it's very small because we're making this approximation.
Okay, you are making it. Sure.
We make that approximation,
Okay.
then there's, in general, they need not be small.
Yeah.
In general, no. But if we make this approximation, then they are very small. Okay? Okay, now, we have four covariant quantities, right? You can identify four covariant quantities. We have on one hand rho and h, and then we have psi 2 and sigma, right? Now, notice that these two are common to FLRW. FLRW model has density and has the Hubble expansion, right? But FLRW models have no shear, have no electric bypass. So these two are common to FLRW, and these ones are distinct, right? These ones are what makes these models distinct from FLRW, right? Now, you mentioned that there was some inconsistency in the models. Can you say why is it inconsistent?
No, I just found that these equations where you wrote h parallel is equal to h minus 2 sigma, and h
Yes.
perpendicular is equal to h plus sigma,
H parallel,
is equal to h minus 2 sigma,
yes.
and h perpendicular is equal to h plus sigma.
So why this is inconsistent?
Well, because now h is equal to h parallel plus h perpendicular, so you add them, you don't get h.
Yeah, but you don't have, you don't, yeah, okay, I see your point. If you, then H H is not, yeah, I see. If you add them, then you get 2H minus sigma, yeah. But H is not the addition, so maybe my error was this. From here, how do you get H? See, you have H equals H per minus sigma. You substitute this in H parallel, so you get H parallel equals, or maybe, yes, H parallel equals H per minus sigma minus 2 sigma, and it's H per equals, so H per minus 3 sigma. And from here you obtain sigma. Here you obtain that sigma, 3 sigma, is equal to H per minus H parallel. And you do the same for H, and you obtain the H. Maybe it's not true. Maybe, well, here you can also eliminate. The point is that these are very simple equations. You can always solve them for H and for
So
sigma.
why not write it as H parallel is equal to half H plus sigma, half H minus sigma? It is
Yes,
possible.
yeah,
Yes.
yeah, that will do, yeah, I was thinking.
Yeah, it's just a matter of solving. That's all. Maybe I had it wrong there.
One of them would be symmetric and other would be an anti-symmetric part.
No, there is no anti-symmetric part
So
here.
look, it's a way of writing just.
Yeah. This is just very simple equations. Like, again, we eliminate sigma. Sigma is H per minus H. You substitute it in the other one. H parallel equals H minus 2 that multiplies H per minus H sigma. And here you obtain H, have 3H, yes, because minus 2 is H plus 2 sigma minus H per, and then you have
2H
3H,
2H
Where's the French book?
it's minus 2
2H.
sigma, 2H,
per.
2 per, here, yeah. Okay, so 3H will be H per plus 2H per. That's H. And then you divide by 3. Okay? The point is you can always obtain H from these two. Okay?
So H need not always be H parallel plus H perpendicular.
No, yeah, if I wrote that, that was wrong. This is the right form. But the point is you can always decompose, you can always find H and sigma. Okay?
Yeah, it can vary with means what you have written earlier, and you can adjust it. What you do.
Maybe
Yeah.
I did not write, it was an error. I'll see that in the transparencies. But the point is you can always recover.
Yeah, yeah.
Okay? So this is now for FLRW models, again we have that rho depends on time. We can identify mu with the initial density. Mu prime is 0, and this is what we get for FLRW models. So both quantities they look like exact perturbations around the following scalar quantity. Notice that we can call this quantity mu divided by AQ. We're going to call it rho Q, rho sub-index Q, because it's an energy density. For the time being, it's just a name, but this name will be justified. For now, it's just a name. So notice also that mu can be expressed as m divided by r cubed, right? This is providing an interpretation for m as a sort of mass. It's a mass that is obtained by a sort of density, which is mu q. We're going to show that mu q is an average density. But we have to show that carefully. Meanwhile, it is behaving as a sort of average density. And this quantity, this rho q, has very nice properties. For example, it has units of energy density, and it also has a nice covariant interpretation, because notice that this quantity, rho q, is, which is also, it is mu divided by aq, and it is m divided by r cubed, and it is the sum of the psi 2 scalar times 4 pi 3 times rho. But since we know that 8 pi rho is the richest scalar, this quantity is psi 2 times 1/6 of the richest scalar. So this is actually an invariant quantity. It's the same in every coordinate transformation. In every coordinates will be the same. And it is a very important term. In fact, in something I have not mentioned, which is probably a useful bit of information, is that Schwarzschild metric is a particular case of LTV models. It is, if you take the source of an LTV model is dust, right? And there you have a dust distribution. Now what happens if your dust distribution becomes a delta, Dirac delta? Then LTV models reduce to Schwarzschild. But Schwarzschild metric expressed in comoving coordinates, the coordinates that correspond to geodesic observers in Schwarzschild, right? And then in that case, m reduces to the Schwarzschild metric, to the Schwarzschild mass. And this term, Schwarzschild mass divided by r cubed, r would be the Schwarzschild radial coordinate. It is related to the to tidal forces. Well, okay, I'm not going to go much into this because this will open a very large parenthesis, and probably you are going to have a course on black holes, and I think Schwarzschild metric will be very well discussed in those courses, so I'm not going to go into it. Okay, computing gamma. We still need to compute gamma. See, we know how to compute the analytic solutions we have are very easily translated into this parametrization. I'm going to show now how. Probably it's important to see that. See, let me write again the analytic solutions. We're going to transform them into this parametrization so that you see that this is very straightforward. So remember we had something like, first the equation that we had to solve was r dot squared equals 2m by r minus k. So this, it is a dot squared r squared equals 8 pi by 3 mu r cubed over a r minus kappa r squared. I'm just substituting things, right? Now here, all these things go away, right? And we get this equation, which looks very similar to the FLRW equation, right? Right? Just substitution. Okay. Now, we have this equation. Let's take the case negative k. Negative k is the same as negative kappa, right? Because k is simply kappa times r squared. So the sign of k is the sign of kappa. Okay? So we had this equation. We had r equals n divided by k times cosine is 1. And we have t minus tbb equals n divided by k 3/2 sine. Right? Yeah? This is what we have. Now, immediately, we see that this is A times R. Then what is N? We have this. But notice how here r cubed cancels r squared, and they cancel this one. So this, what we have is A. What we have is A. This is the solution. Remains the same. Instead of M and capital K, we have mu and kappa. Okay? And the same thing happens here. Here, this would be T minus TBB equals 4 pi thirds mu. Then we have kappa, and then we have r cubed. R squared, so 3/2, and then right. But these two cancel, because here is r cubed and r cubed. These two cancel. And what we have is this. All right. These are the solutions.
Kappa to the power 3/2.
Sorry?
Kappa to the power 3/2.
Yes, that's right. These are the solutions. Here. Kappa. So the same solutions we use, right? Exactly the same solutions. So since we have these solutions, we also have a solution for, as we show you, for gamma. We already had something like this. We had something like r prime equals n prime by m minus k prime k multiplying r, and we have some stuff here multiplying r prime. So this will give rise to the form for gamma, as we are going to show now. gamma. We have analytic forms for rho and psi 2, but we need gamma. Now, you can see we need gamma, otherwise we cannot compute this quantity. Now, for lambda equals 0, remember, if lambda is not 0, gamma has to be computed numerically. In fact, these solutions, R and T, follow from integrating a quadrature, from integrating something. If lambda is different from 0, that has to be done numerically. But if lambda is 0, then it can be done analytically. So look at this. This is the expression we had before, right? I just divided everything by R. So now we make these substitutions, and this becomes, this is given in this form, right? And of course, this T is this integral, and this A dot A is this quantity. But we don't need to do this integral because we have the solutions. You simply substitute this, mu and k, you choose. These are free parameters, right? Big Bang time, you also choose. But we already have an expression for T minus TBB. It's here, right? We have this expression, okay? And we have this expression because we choose TBB. And then we have this expression here. We don't have to, this quadrature is already done here. It's already solved here, okay? So we have A dot times A, and we simply substitute the forms for A. Here we have A, here we have A, here we have T of Big Bang. So we just substitute this and that's it, okay? So we can also compute things with this parametrization in a very similar way, right? Okay, so this is interesting because remember that these things, I think this is wrong. This thing is wrong. There needs to be a, this thing I have to correct. But nevertheless, this one is correct. This is incorrect. But notice how you can compute these quantities also. And notice how, if these gradients are very small, these gradients, I mean, the gradients of our initial value functions, of our parameters. If this gradient and this gradient is very small, this term is very small. This term is very small. This term is very small. So essentially, under conditions where the gradients are very small, right? And notice that they are dimensionless gradients because they are being multiplied times R. So they are dimensionless quantities. See? Here there's also a dimensionless quantity, right? If these things are very small, then gamma is almost 1. And it's almost FLRW, right? Okay? And of course, if lambda is different from 0, then you have to evaluate this quadrature, and this is no longer true. It's more complicated, right? Now, another interesting thing is that if you compute this quadrature and use the, if you use the implicit form, then you can express the Big Bang time as a function of the other two. See, let's see it mathematically. F is something, right? You compute it. It's not the parametric form, it's the implicit form, right? You also have it there. I'm going to put it in the blackboard, but it's also in your notes. See, there is an implicit form that will give you t as a function of a. Instead of a as a function of t, you have t as a function of a. And you compute this. Suppose you already have an analytic expression for this. Okay? Now, evaluate, this is valid for all times, and this is all A, right? Okay. Now, what happens if we set t equals to t0? If we set t equals to t0, then A becomes 1. Why A becomes 1? Because remember that we're making this coordinate choice. We're making this coordinate choice. We're saying R of 0, which is R t0 equals R. Okay? So what is A? A is R over R. So what would be A0? Okay? This is a scale factor that in the initial surface becomes 1. So it is illustrative. It is very illustrative to write the metric at t equals t0. The metric the metric in general is ds squared equals minus dt squared plus a squared gamma squared dr squared 1 minus kappa r squared plus r squared then the this is the metric. So at t0, dt is 0, right? So let's call this metric 0. This metric, let me write it here. This metric would be A is 0. And what is gamma? If A0 is 1, then what is gamma? Gamma is 1 plus RA prime over A. And if A0 is 1, what is A prime? 0. So gamma 0 is 1. So the metric becomes see, the metric in the initial time slice, it's a metric whose curvature is given by this. The Ricci scalar of this three-dimensional surface is going to be simply. See the Ricci scalar. The Ricci scalar in general is going to be, well, this we will compute later, but at t equals t0, we have this relation. The Ricci scalar here is simply kappa. So this thing kappa is a Ricci scalar of the initial time slice, right? It tells you the curvature of this slice. Okay. Well, let me look at the implicit solutions. See. See. We have this equation. And this is the same, generally. Okay, this is the same as this one. Same. So I already showed you the parametric solution. Now let's see the other solutions, the implicit solution, because we have to do this integral. Right? This is the integral we have to do. Let's consider the case of negative k. Negative k means this. Okay? Okay? So the implicit solution was something like t minus dvb equals it was something like m over not sure, something like this times but let's write that in this way. Easier.
Sir, can you please write in a larger font?
Sorry?
Can you please write in a larger font?
Little bit bigger.
Bigger.
Okay. Is this okay?
No, sir.
It's very far, no? So, but maybe you can shift it over here, no?
That's it in
This. Times square root of. Is this okay? These are given in your, and you can also obtain from the parabolic, from the parametric solutions by eliminating the parameter. Can people see?
Yes, sir.
Yes? See? It has this form. Sorry? Yes, this is inverse cosine, hyperbolic inverse cosine. This. Now let's put it into our new variables. To our new variables. It's, we already know that this, once we substitute this, the r here is an r cube, and there is an r cube here, and in a 4p by 3. Okay? Because we are going to substitute this function. Here, we make this substitution. We say r equals AR, M equals 4 pi by 3 mu R cubed, and K equals kappa R squared, right? Just make the substitutions. And here we get kappa, the 3 halves, by 4 pi 3 mu, right? First term. And then we have something like this. We have square root of mu where u is going to be identical to m 4 pi 3 R. I think it's the opposite. Let me see something. Yeah, this is the opposite.
Duster is there.
Yes. This is the opposite. It's K divided by M. Over R. Yes, it's what's the opposite? It's like this. Okay. So it is mu. No, it is kappa R squared 4 pi 3 mu R cubed AR. And if you see all the R's go away, and then we have kappa over 4/3 mu kappa absolute value 8, right? So this is our solution, right? Okay. Now, what happens if we, in this solution, if we set t equals to t0? Then we have a0 equals 1, okay? Right? So what we would have is t0 minus tbb. tbb is a function of r, right? This will be equal to 3 kappa to the 3 halves by 4 mu multiplying u0 times 2 plus u0 minus hyperbolic sine inverse 1 plus u0, where u0 is identical to kappa, 3 kappa by 4 pi. Okay. So this is a function of r. Once we have chosen mu and kappa, this is all determined. Only at the initial slice, because at the initial slice, A becomes 1. So A plays no more role there, because it's 1. Right? So all these are functions. Once we have chosen kappa and mu, this is all determined. Right? So we can write Big Bang time equals T0 minus all this.
Yes.
Minus all this, which is right? And so, in this parametrization that we're using, the Big Bang time is no longer an independent function. It is given by the choice of the other two. And this is possible because of this coordinate choice, right? Because of this coordinate choice. See? Because of this coordinate choice, then only two functions are necessary. If we had not made this coordinate choice, then TBB would still be an independent function. But this is very convenient for the following reasons. If you are going to set up a model, then you know that mu is a sort of average density. And kappa is a sort of average curvature, right?
Yeah.
So you have an idea, how would you prescribe an average density? Suppose you want to model a galaxy. So how would you imagine the density should behave? Something like this, right? You imagine density in the center, large, and it is decaying. It decays to a certain background value. And how do you identify the curvature? Well, in a similar way. Curvature will be either very low or very high, and it will somehow decay. So intuitively, it is better it is not so difficult to guess the form of the average density and the average curvature, right? And once you have chosen them, you determine your Big Bang time. This is much easier than if I tell you, sir, what's the Big Bang time function? What's the Big Bang time function? What? I don't know, it can be an accordion, it can be anything. It's very complicated to guess what's going to be the Big Bang time function, right? So this parametrization is very convenient because the two functions you have to choose are intuitive, right? Are intuitive, are easier to choose. And then the Big Bang time the Big Bang time follows from that choice, right? So this is extremely convenient. It's an extremely convenient way to work with the models. Now, a lot of astrophysicists, they keep choosing the Big Bang time function. They choose it in order to comply with regularity conditions, because I don't know if you remember in a slide before, when we were talking about absence of shell crossings, the Big Bang time gradient had to be negative. So they choose it like this, and they invent some mathematical formula for it. So that's, that can be done, but it's easier to do it like this. Here, we see another interesting question. Are we forced to have a non-simultaneous Big Bang? Are we forced to do that?
So
See?
here the U is related to M and R.
What?
U0 is related to
Yes.
M and R.
No, U0 is here.
Yeah, U0 is there, but it means I'm talking about not U0 but U. Then it's related.
Yes, U is a factor multiplying A. But in the initial time slice, A is 1.
Yeah.
So mu becomes only a function of the two variables. Right. Now, here we have an expression for the Big Bang time, right? So we are assuming the Big Bang time is a function, right? The Big Bang is not simultaneous. But suppose we run into somebody who says, no, I want the Big Bang time to be simultaneous. Can we please that person? Look at the mathematics here. What would happen if we force the Big Bang time to be simultaneous? Suppose we say we want the Big Bang time to happen at a constant. Let's call this constant constant. Is it possible?
This should be zero.
Eh?
Then this should be zero,
No, it's not going to be T0. No, it cannot be T0. T0 is the initial time.
Not T0, not I'm talking about T0.
It can be 0. It can be set to 0.
No, I'm not, the next term, what?
What next term?
Minus, second term.
No, it can. The second term cannot be 0
yeah, it
because
can.
then the Big Bang time would be your initial slice. And in your initial slice, you cannot have a singularity there. You need the initial slice has to be regular because you are putting your initial data. So it cannot. No, it cannot be. We cannot have. This has to be different from T0. It must be different from T0. Also, not only it must be different, it must be earlier, right? Because we are assuming this is our time axis, and this is radius. So here is t equals t0. So the Big Bang, whatever it happens, has to be before. It cannot be afterwards. Suppose the Big Bang time is here, so your evolution is only in this way, so it would be sort of silly to have initial data before the models begin, right? It's like if I have an appointment with you at 5 o'clock and I show up at 4, and then I say, oh, you came late. That's not possible, right? So it has to be before. Has to be before. So whatever this has to be satisfied. The Big Bang time has to be before the initial surface. Right? It can be something, it can be somewhere here. Right? But it has to be before. Now the question is, can the Big Bang time be a constant? It has to be a constant that in fact is less than that. Okay?
Yeah.
Can it be a constant? Just look at the definition. What happens if we set it to a constant? What we would have is TBB 0 equal constant being equal to T0 minus some horrible function of mu and kappa. Right? Can this be constant? Yes or no? Why not?
If that horrible function is a constant.
No. Cosmological constant is 0.
If that horrible function is a constant, then it can be a constant.
Sorry, what?
If that horrible function is a constant, then
If that function f is constant, then
Well, of course, what you would need is this thing, this implication. Well, this. See, this reduces. If we set it to a constant, this reduces to an algebraic equation, right? The algebraic equation would be T0 minus the constant equals horrible function. T0 minus this is equals horrible function, right? But is this possible? Of course it's possible. It's just what you have to do is to solve this constraint in order to obtain mu as function of kappa. Depends on the constraint. But for this constraint, I guarantee you that it's possible. Right? This means, this has important implications, because it means that mu and kappa are no longer independent. This means that if we set the Big Bang time to a constant, then the parameters have a single free parameter. The models have a single free parameter. Can either be kappa or can be mu. And this, and then you have an extra constraint that has to be satisfied. right?
Then all gamma n will be a function of one parameter only.
Only one parameter,
Yeah.
yes. Will be a function of only one parameter, right? In fact, you can also set up the Big Bang time. Something that is very comfortable is to say that T0 is 0, and then or maybe the opposite. We say T Big Bang time is constant and is 0, right? But then if this is 0, and then your constraint, so it's very simple. Your constraint is then T Big Bang time 0 equals, if T equals, no, it's already set to be 0, then your constraint is this. This is a constraint you have to, okay? And if we want T0 to be present cosmic time, then this has to be equal to 13.7 gigayears. And that's it, and you solve everything. Okay? You solve this constraint. And and your diagram would look like this. Here, Big Bang in T equals 0, and here would be your T0. That's it. Your models are evolving. It's possible to do that, right? You can also set T0 to be 0, and then your Big Bang time would be negative. That's possible. All these options are possible. Depends on the numerical problem. But this is very common. People do this a lot of times. Now, one question that people might ask, how long do we have? Like 0, right? Time out. Okay, so just this slide. So one question people ask is, why should the Big Bang time be forced to be simultaneous? Yeah, well, it's very important questions, right? If the Big Bang time is not simultaneous, then your model will be very inhomogeneous in early times, right? Why it would be very inhomogeneous? Because this is an important issue. Here it is. This is an important issue. Suppose Big Bang time is non-simultaneous. So, here is your Big Bang time. It's a singularity. Here, A equals 0, density goes to infinity. Right? So an observer emerges from here, right? And then a neighboring observer emerges from here, right? So this neighboring observer is here, and he makes, he or she will make observations. This is the light cone, right? And so, how is the density behaving along this surface? Along this surface, which is some constant time, here density is infinite, right? And here density is finite, right? So this observer, in one direction, would detect infinite density, and in another direction, harmless finite density. So the space-time would be extremely anisotropic for any observer nearby, right? Because in one direction would be infinite density, and in another direction would detect also infinite density, but a larger redshift. At the same redshift, redshift is distance along the light cone. At the same redshift, in one direction, you would detect a horrible explosion, and in the other direction would be nothing. So these observers near the Big Bang would detect extreme anisotropies, right? Right? Now, we know Well, we think that the early universe was very homogeneous and very isotropic. Otherwise, we wouldn't have the CMB. The CMB is a relic from the early universe. The CMB emerged when there were no galaxies, no clusters of galaxies, no planets, no Roberto Sussman, no Bosch, nobody. See, the CMB already emerged from there. So the CMB is a relic of the early universe. And the CMB is practically isotropic. So it is extremely difficult to justify the CMB if the early universe was violently anisotropic, right? So the assumption of a simultaneous Big Bang removes this. Why it removes this? Because the picture would change. The picture would change very much. If the Big Bang is simultaneous, then these observers do not detect anisotropy. They would detect horrible explosions everywhere. It would be isotropic. So a simultaneous Big Bang is a isotropic singularity, right? And it is consistent with our notion that the early universe had to be almost isotropic. Then there is another issue, inflation. You know, inflation is a process with extremely fast expansion, and extremely fast expansion really isotropizes and homogenizes. See? It's like if you have all sorts of rugged balloon, and suddenly you inflate, what happened with all this ruggedness? It is ironed out, right? So if there was inflation, which some people take as an article of faith, inflation hasn't been proved. It's a consistent theory, it's a good theory, but it might not have happened. Don't be fooled by that. While if you are with a big professor, big ego, and he says, was there any inflation? Then they say yes, but inside of you, you say, I say that because you are big ego. But really, it's not true. If you have a chance, you challenge that authority. But we have to challenge it with arguments, not say, you big ego. That's not scientific argument, right? Okay? So, Big Bang, simultaneous Big Bang solves this problem. So it's favored. Many people like it. However, notice that here we're assuming that Big Bang time prime, the gradient, is zero. Mathematically zero. Need not be exactly zero. It can be, we can say that this is non-zero, but small. We can say that this is non-zero, but very small. And then it's still okay. It's still okay, because yeah, you have some anisotropy in the initial universe, but very small. But mind you, the CMB is not perfectly isotropic, it has small variations. So we can also choose small variations of the initial time, of the initial Big Bang, right? Now, this is not so harmless, this is powerful. Because if you do that, then you still have two free parameters. If you say mathematically Big Bang is absolutely mathematically simultaneous up to 570 orders of magnitude, then you have only one free parameter. But if you say, no, it's not simultaneous, it's almost simultaneous. How big? As big as the fluctuations of the CMB. You can say that this is of order 10 to the minus 3. Then it's 10 to the minus 4, or to the minus 5, whatever. Then it's safe, no problem. However, mathematically, you don't have to solve this horrible constraint. You can still have your two free parameters. So the best approach is not to assume that it's simultaneous, but that it's almost simultaneous. But astrophysicists are so dumb that they take this to be zero mathematically. They think they are simplifying. And they are not simplifying because it's not necessary. See, there are how many things in physics are measured with extreme precision? In particle physics, you have things like that. Measurements of masses of particles, they are measured with extreme precision. The simultaneity of the Big Bang cannot be measured like that. We're talking about something macroscopic, something classical. And even the early universe was simpler than the modern universe, but it was not so simple as to demand that it can be measured by such precision. So it's quite safe to do this. And mathematically it's also helpful because you have two free parameters. Right? Anyway, I think we're about to finish. Let me just finish this thing here. I think there is another one here. Yeah.
An observer at a vertex of an equilateral triangle watching a black hole and at the same time watching the universe, will he observe anisotropy?
Of course, because the Big Bang is far away, and the black hole in terms of light cone. Where do you want the black hole to have occurred? When? At 1/2 of the age of the universe?
Now it's
Nowadays, I don't know. No, but remember that distances are translated into how old. If you see a star 1,000 years ago, you're seeing the star as it was 1,000. You're not seeing it in your time slice. Okay. So black hole will be seen in a time slice that is much before the Big Bang. So yeah, no, of course it's anisotropic. Now,
so
here,
what is the problem with Big Bang not happening simultaneously? Of course, I can have an observer who is looking at the universe at his frame and looking at the Big Bang. He is observing anisotropy, and the things could be simultaneously there when the black hole, even with that.
No. You are looking for cats with 3 legs. It's much simpler. The observations from the Big Bang are very far away in your light cone. In fact, we can't see the Big Bang.